Well, hello, fellow performers. I hope everybody is bringing full energy today because we are going to talk about something that really excites me. Web performance beyond client side. Client side. We are heading for a journey from the user to the server gateway and then to application layer, and we are not going to stop until we hit the bare metal, which is a very interesting topic for me also. So my name is Alfonso Moure, and people usually knows me as Mo, M-O-U, and I'm based in Spain, as you can see for my excellent accent, speaking in English. And I've been doing technical SEO since 2004. So I've seen a lot of things during those years. So I wanted to start saying this. The fastest server is the one that doesn't run. Why? Because every fast server you've ever met is fast because it's going to avoid the work. Cache that answer before the apps wakes up. That's very important. We are going to talk about a lot about this in this presentation. And servers don't get faster; they get better at not running. That's the important aspect. And yet, most of you have a cloud bill that goes up every quarter, and the server gets bigger, the plans get fancier, but it also gets expensive. That's not a coincidence. Your server is expensive because it's busy being expensive. It has redundancy, security, scale, and none of those are speed. So if expensive doesn't equal fast, what does? Let's explore how this works. A user taps something in your phone, or well, in their phone, not yours. The request travels through the network into the edge, through your gateway, into your application, and maybe then into a database. And the response travels back. This goes through three regions. First, the client side. This is where the browser lives. Then the middle side is where the network is going to route the user and the request to the server. And then, of course, the server side. TTFB adds up to your total loading time and accounts for a huge part of it, as we are going to see here. And why does it matter? Because TTFB is the floor of Web Vitals. All the metrics that you are going to work in the front end are their floor is the speed of the how the first byte comes back from the server. So uh, my line when I am trying to optimize TTFB is in 700 milliseconds. Google says 800 is good, but I prefer to be a little tighter because you don't know what could happen. So I prefer to have some space to work with it. And in that case, I treat this as a problem when TTP is above 700 milliseconds. Uh, Two main suspects when the TTFB goes over the line. Either the user is too far from the server, geographic, physics, the speed of light, stuff like that, or something inside the server maybe is not working properly, it's slow. That's a big label everyone hides behind server issues, as you may know. So it sounds very convenient to use the server issues label. Convenient, and also it led us to a black box full of monsters you've never met, maybe. And today we are going to open those boxes and see what is inside of them. But first, real numbers. Yes, TTFB on the web is improving overall, slightly, maybe a little, moderately, and still almost 60% of mobile requests are outside the good enough zone. That's the world our users in every day. But everything, like I said before, is inside a black box. And most teams treat that TTFB as just that, a black box. Drop a cache in front of the black box, hope for the best, and move on. That's how most of these type of problems are treated. But it's not just one box. It's many boxes, one above the other, all the way down. And this is what we are going to explore today. So we are going to open the first box. What can we find inside that first box? We are going to find 7 layers of boxes. From the surface, that's where the user lives, and then to the bare metal, the hardware. The first layer is the surface. This is the browser, like I said before. The second one is the global edge, is where the CDNs are the external cache are living. Third, the gateway. This is where the servers, this is where the perimeter of the server is located. It's where all the security layers, routers, etc. are located. Four, the logic. Finally, your application code. Here's where most developers live. And here is where all the fancy stuff like WordPress, Magento, etc. pass all its time. And of course, this is also the home of quite a lot of dragons. I talked before about the monsters. Here we can find a lot of them. Five, the memory. In this case, I'm talking about the memory located at the server, not the database. The database is the following layer. And here, this is another favorite home for dragons and monsters, like we are going to see. And finally, the bare metal, the hardware. Each one of those is a black box for everybody. Depending on your knowledge, you can go deeper or stay on an upper layer. Before we go in, we need a method to work on each of these boxes. I like to describe my evaluation framework using a triage method. For example, in this case, the first, we can divide this method, this framework, in 3 modes of working, in increasing friction, depending on what you are leading with. The first is the do. What you verify yourself with the access you already have. You don't need to put tickets to other people. You don't need to do any meeting, and you don't need to spend money on that. Just your computer. The second is the ask. A specific question to your team, your platform people, your provider, etc. The cost, the time to make those questions. And the third is the demand. What you put in contract, an SLA, or a monthly report you are requesting to external providers or your IT department. It is important to remember that you always need to start with do, okay? Because you need to, I prefer to try to stay in control of what I am doing. So when we move forward with this presentation, you're going to see that I always focus at the beginning with the do. Okay, so layer 1, the surface. This is the browser, like I said before. This is where Web Vitals live, and is the page the user actually sees when it's interacting with your website. And most performance content lives here also. Most courses, blog posts, consultants, etc. Most technical SEO recommendations live here in the surface. As you know, because there's a lot of content here in Performance Observer about how to improve the performance of the front end. This is a box with a lot of knowledge surrounding it. In this case, I just want to highlight that I prefer to work with real data to make decisions. I think it's important to use lab data, of course, and automatic testing, of course, but there is nothing like logging real conditions and being able to read that information. So I'm not going to talk a lot about that layer. The second layer is the global edge. The request, like we saw before, leaves the browser and starts its journey to the server. Before it ever reaches it, it almost certainly hits a CDN. Cloudflare, Akamai, CloudFront, pick your poison. This is the geographic layer. The speed of light is the limit, like I said before. So let's open the box. What's inside this box? Remember the opener of this presentation? Same idea here. Your fastest server is the one your users, and especially the web crawlers like Googlebot, never have to reach, because the edge already answered the request. The most important concept here is the points of presence. Actually, I don't know how people pronounce this in English, if it's POPs or POPs, but whatever, points of presence. Okay, in this layer, geography is your floor. Keeping close to the user or the bot is the main key of what we are doing here. For example, a user connects from Sao Paulo, and the CDN decides that the closest point of presence is in Madrid. That's frankly stupid. That's 200 milliseconds before anything else happens. So because we can surpass the speed of light, like I said before. So this is an important point. So how I do manage to implement the triage framework here? First, the do. Pull your CDN gas hit ratio. This is the most important part of this analysis. And everything below 90% of static assets being served from the gas, you have a problem. Okay, you are leaving money and milliseconds on the table. So that's the first thing to work on. Second, the ask. Where are our top users actually located? This sounds like a very basic and stupid question, but I'm always surprised about how many people doesn't ask this key question of the project. Okay, and the third is demand. In this case, usually the SLA contracts that you may sign with a provider are usually focused on uptime. I think that's intelligent. You need to do that, but also you need to work on the points of presence. Where are they going to put your information to be served? Usually, this is something that if you are working directly with, I don't know, Cloudflare, you are able to set that up by yourself, but you are not always so lucky to be able to set those things by yourself. So it's important to think about them. So layer 3, the gateway. The edge couldn't answer. Okay, so we need to go into the server. So the request enters your perimeter. This is like just as I said before, is the layer that surrounds your server and your execution power. And before any of your code runs, there's a collection of gatekeepers, and your request needs to go through them. So what's inside our black box full of gateways? Here we find at least six gatekeepers, each one looking for something different, each one charging milliseconds for their service. First, in most cases, we find a load balancer in charge of routing the request to a healthy destination. For example, if your server is based on a CPD, a place full of servers, usually the balancer redirects your request to a server that has enough resources at the moment to attend the request. Then we find the TLS handshake to negotiate the encryption, which protocol is going to use to communicate securely with the user. It could take about 20 or between 20 and 100 milliseconds, depending on the protocol that you are using. So this is not trivial. And then, if the people in charge of security has done its job, that's not always the case, we should find a web application firewall or WAF. Here you may expect 1 to 50 milliseconds, depending on what they are doing inside that another black box. Sometimes we find a rate limit control, as you can see here. This is usually used to control users that are going above their budget, making requests to the server. It's usually very, very fast, between 1 millisecond and 5, depending on the platform. And everything adds up. On a cold connection with heavy security rules, you can spend at least 200 milliseconds connecting just before anything is executing on the server. So this is tricky. As you can predict, like I said before, the WAF box is also a black box in itself. And most teams enable everything by default inside that box. So it's usually a mess. And then generally, nobody audits the rules from time to time inside the WAF. So this is usually a quick win, okay, to check what is happening inside that box. So first, also, we are going to execute the triage. First, the do. I usually recommend executing an SSL labs scan I know this sounds very simple and very easy, but it usually leads to very interesting opportunities at the beginning of the project. So it's interesting to do so. Whoops, sorry. Um, yeah, and second, ask. This is the most important question of this layer. When was the last web rule audit? So when did, for the last time, the security team or the security people did check those rules that are configured in the web application firewall? This is a key aspect of this layer. And demand. Put the WAF latency, your provider's SLA. And yes, I keep banging on about the WAF, but this is always a source of problems. So please check what you are doing there. And we arrive to layer 4, the logic. We have crossed 6 gatekeepers, 200 milliseconds have been spent, and finally we arrive to the server application. This is where most developers live, and this is where everyone blames first about what's happening inside the server. And I have to say that they are often right, sometimes they are not. So, what can we find here? Inside the logic box, we first find the operating system layer. Generally, it's a Linux system. Usually, it's a Microsoft one. I usually work with Linux. I don't remember how to use Windows actually, and we usually are not able to interact much with that level, depending on our provider, but it's not very common. And then we go to the runtime level. Here is where Node, Python, PHP, .NET are doing their stuff. And I often find packages years out of date. For example, the jump between PHP 7 and PHP 8.3, night and day. Okay, you can find a speed up between 2 and 3 times of performance. I don't know why people continue using PHP 7, but because I usually program in Python and I'm stuck with 3.10 and they are with 3.14, okay, I can be too rough with them, but I don't know why. So then we have the framework level. Here is where Django, Ruby on Rails, Laravel, Spring, Nest.js, etc., are living. It adds an overhead depending on the platform and the runtime you are using. The choice made 5 years ago may still be costing a lot of time and, of course, money. So it's important to check what is happening there. And then we have the middleware level. This is where all the login, session control, application security, authorization, etc. is living. And most applications have 10 to 20 middlewares. None of them are measured individually. Okay, so that's also a huge point to check. And finally, we have our code, the business logic, the code you actually wrote or something or someone wrote for you. So actually, someone or something today, but yeah. Hopefully it's fast or it has been tested for performance, not just for correctness, but who knows. So how we can measure everything here in the app layer? I usually use an APM, application performance monitoring tool. In this case, I usually recommend New Relic. I'm not going to go deeper on this because we can spend here 4, 5, 6 hours. It's a very good tool. It's a little expensive or very cheap, depending on how much are you going to be able to put in practice. But I recommend you everyone to check it. So how do we apply the triage framework here in the logic layer? As always, first start profiling your slowest endpoint. Of course, to do so, you need to be profiling everything. It's better to do that. And that's why the APM, New Relic, like I said before, that's the one I usually use, is a very good option. Also, check your runtime version. Like I said before, you can expect huge impacts on what you are seeing. Second, even if your runtime is up to date, and this is important, ask whether we can upgrade to newer versions, even if those versions are still unstable. Why? Because everything may be working fine right now, but maybe next year you are going to need to do that upgrade and you may not be able to do so. That's important. And third, the demand. As a non-negotiable to yourself or to others, I always set up my APM to show breakdown reports for both users and bots, split it, in a split view. Why? Because usually you can find opportunities comparing the data of how the users are measuring while they are interacting with the website compared with the, for example, Googlebot or Bingbot. That's an important split to do. So we have surpassed 4 layers. We've been making the work faster. We've been working to make smaller handshakes, linear middleware, better runtime, faster code. From here on, we change the question. We are not working to make this work faster. We are going to try to avoid the work at all. So we're in the layer 5, the memory. If the previous layer asked how do we run faster, this one asks something different. How do we not run at all what we are doing? So what's inside this box? We have 3 places where memory lives, plus a fourth, but we are going to talk about it later. In-process cache, this is the first one. It lives inside your application's own memory. It is very fast, the fastest actually, but of course, it is also the smallest and the most expensive. It is lost when the process dies, so it's not very useful in production when you are trying to handle huge amounts of information. There is no such thing as a freelance. Okay, so it's expensive, it's small, but it's extremely fast. So what I recommend to put on that memory? Data that you are going to show constantly on the website. Okay, instead of using another layer of cache. The second one is the out of process cache. In this case, I usually use or Redis or memcache. They are shared across instances and they are not as fast as the in-process cache, but it's much faster than other types of memory. So it's interesting to keep them in mind. And also, even though it's slower than in-process memory, it's still quite fast. Okay, I know that I'm repeating myself, but it's important for example, I usually use Redis as a method to control redirections on a website, because usually if you have a very big site and you need to redirect requests, Redis works very fast to manage that, okay, to find what is the valid destination for a request. So then we have the operating system memory. This is handled by the kernel, the Linux kernel, so you don't have to do anything about that, but it's also very fast, much faster than the database, of course. So what can we do here? First, the do. Pull your internal cache hit ratio per route. This is important because normally when you use a dashboard where performance information is shown, we usually check them as a global data or at a content type level. In this case, I recommend usually to do that at the URL level. Also check if there is anything that is being called and returning lower hits because application has invalidated it. Here I also have a doubt when I prepare the presentation, because I don't know if the correct word is invalidated or evicted, actually. But this is a technicism. I will check later. So this is the do. What do we have to ask? How are we invalidating or evicting the content? Are we using the default policies, or does the application have the capability to optimize its use? This is important because we usually don't let programmers handle the invalidation or evicting policies, and they usually lose a lot of opportunities to optimize the result. Okay, so I usually recommend to let them modify this. And also, when optimizing this layer, there is a quick win that you have to keep in mind. Instead of storing in the cache the information when you are generating it, it's more precise and and offers the most cost efficiency relationship to pre-calculate everything that you need to show and store that in the cache before. Okay, it's like a pre-compute on write instead of on reading. This is important because when a user visits a site for the first time, you're going to be penalized if you do the other one. Okay? So, layer 6, we are in the database. This is where the data actually lives. And if memory was about declining the work, this is where the work was going to happen anyway. If you reach the database, it's going to do something. So what's inside this black box? Whenever a database engine receives a query, it needs to parse it to understand what it means, and then it plans how to execute it. The plan figures out in advance which tables to read, in which order, and what indexes to use to speed things up. This is where most of performance gains are hidden. Okay? The same query can be 1,000 times slower with a bad plan. So usually, this is where I get most of the improvements. Then when the engine executes the query, it usually collects a collection of indexes that helps find the information quicker. Instead of running through millions of rows, it just computes where to find the necessary information. Living above all of this is the buffer pool. This is something you don't need to care much about because this is handled by the engine, but depending on how the query is written, you are going to impact differently the buffer pool. Okay, so I recommend you to read something about this because it's a very interesting topic. Um, and uh, and I was going to show you a real case, in this case, to explain this. On one project, we found that there was a query that took 5 seconds to run. Yes, 5 seconds is a lot. I know. I can see hands going to faces right now. Uh, but it's important to know that that query was executed only about 0.5% of the time of the day. So it was not very huge, but the impact was important. And it was lagging the whole system down. After analyzing the structure of the database and the relationship between the tables being used, we found that it was easier to create a new table with new indexes pointing to the 3 tables that were inside that query, and the result was 25 times faster. Okay, so here, like I said before, is also a huge source of opportunities, and you can see those recommendations directly on the APM. For example, New Relic has a very good optimization tool for the database, and I recommend you to check it because it's it's like a dream. Uh, so, triage. First, what to do? First, use the explain analyze. This is a command you can use inside your database engine. It works like a charm and it's going to show you a lot of information even without paying for an APM tool like the one I said before. Also, I recommend to try finding missing indexes. Like I said before, it's also a very good source of time to gain. Second, ask, are you logging your slow queries? If not, you have to do it now. After seeing this video, you have to enable that. And third, what to demand? Ask for a per query latency tracking. This is also normally included with the APM tool, but if you have a provider that doesn't let you install this type of information, maybe it's a good time to do that or to change the provider. Uh, and I also wanted to note that I have never, ever opened a slow app and not found at least one missing index that takes a query from a second to 10 milliseconds. I always see that stuff everywhere. So the last one, the layer 7, this is the bare metal. We have arrived to the hardware where things actually run. And almost paradoxically, this is where most teams stop thinking because of how the cloud services abstract everything that are related with the metal. So what's inside this box? You usually pay for an abstraction, like I said before, in Amazon Web Services, Google Cloud, Azure, etc. Depending on the platform, it has a different name. But behind the label you are paying for, you have what is called a hypervisor. That is the thing that runs all the virtual machines and containers that you are using for your project. And each container has a collection of layers between you and the actual hardware. But of course, what actually runs everything? A CPU, memory, storage, network interfaces. The abstraction of the cloud service doesn't matter in this case. Most teams pick instances based on CPU and memory. And when the app lags behind or dies, they usually log in into the cloud service. They get more CPU and more memory, more storage, and the bottleneck stays there exactly the same. They pay double, fix nothing. So this is how usually things are done. So we uh, we enter the triage phase. In this case, what do we have to do? First, purchase the right size before scaling up. Look for a valid match between the instance shape and your workload. Do not try to overdo it. Of course, if you are in a hurry, of course, do that. But please think before paying more to Google and Amazon. They have enough money already. What do we have to ask? What's our CPU still percentage? That's the percentage of CPU time your hypervisor, that's a tricky word in English, the percentage of time that your neighbors inside the same machine are stealing from your CPU. If it's high, you are sharing a host that's overloaded and your performance is at the mercy of your neighbor. So if you are working on a VPS, that's a very important metric to check. How much CPU are your neighbors stealing from you? Also, are your provider limiting your input and output communications? Maybe if they are doing so, your speed is going to get controlled. So that's a very important thing to check. So we went all the way down and we are going all the way up now to end this presentation. So 90% of slow servers are one of three things. First, missing or misconfigured cache. Edge isn't catching what it could, the application isn't caching specific computations, or maybe both. So that's normally one of the first problems. The symptom, the cache hit ratio is under 80%. If it's under 80%, you have a problem here. Two, unbounded database queries. For example, queries that are not using the limit clause at the end of the query, and also where the where clause is too general, and that's causing a growth over time. Okay, so we can detect that because month to month the TTFB rises as time passes. Okay, and the third one, the wrong location. Like I said before, this is a very important aspect. So it's important to check the TTFB depending on the country you are connecting from. So now you know much more, I hope. So come Monday, I didn't know isn't an answer anymore. And so you can do that. Here you can find a short checklist I prepared and I shared it through GitHub. I have put there the triage framework and also the checklist so you can use it whenever you want. And thank you very much. You can find here information to contact me and ask any question you may have. Thank you.